Okay. So this is what I'm going to say is a way to glue Petronet. In the last 2 years, we looked very in depth to various ways of gluing Petronet together, and basically in the literature there are two main ways that have been devised to glue nets together. So if you have a Petronet, first things first, what do we mean by gluing nets together? The idea is that Petronets, as they are not really compositional objects in the sense that there are no ports or ways to compose them with each other. So what people have done is basically trying to find ways to compose nets together. So since a Petronet is made mainly of like places and transitions, when you glue nets together, the idea is that you want to merge some of these things. So one of the approaches that has been used, in particular by using theory developed by Brandon, by the school of like John Baez and whatever, is about gluing places together. So here the idea is that, for instance, I want to glue these nets by gluing these places, and the final result that I obtain is something like this. So the way you can think about this is I'm basically sharing resources. Since places share resources, this amounts to say, okay, now every token that is in here is also in here, and so it can be consumed by this other net. Then there is another way of gluing nets, which has been developed by other people. Unfortunately, Pavel is not here, otherwise he would be able to tell you way more about this. And this is about gluing nets, thinking about them as synchronizations of transitions. So the idea is that now you basically attach some other ports to this transition, so you have another kind of entity in your net. And when you glue them together, this is what you obtain. And you have to think about this as basically not sharing of resources, but synchronization. The idea is that every time this thing fires, you can see this as a sort of like little message kind of thing that says, okay, now you have to fire too. And so you can conflate the two things into one. Obviously, there are many different models and like flavors to do this thing, but these are like the big two areas that I've looked into. There are also other ways of doing Petronet gluings and whatever, but I'm not going into that for now. But what you really have to know is that both ways of gluing nets are very useful for us. Because, yeah, the first thing is very useful when you want to, let's say, write or model smart contract or something using Petronets, and you say, okay, now this thing really consumes the resources produced by this other thing. Well, this is very useful when you want to say, yeah, actually, I need this thing to, let's say, invoke this other thing and process things together. Another thing that, at least to my knowledge, hasn't really been done a lot around is thinking about the gluing of Petronets with respect to semantics. So as I was briefly saying yesterday, think about these Petronets is really as presentations of three symmetric monodal categories. Every time you draw a Petronet, what we really do is we take the monodal category which is built on that Petronet. These become object generators, and these become morphism generators. And then we map via functors these Petronets to a semantics of some sort, usually types and functions of some programming language. What happened there? Okay, cool. Yeah. So But obviously the idea is that if you have a functor that is basically attaching meaning to this, so you say, okay, now this corresponds to an object A in some symmetric model category, this is B, this is C, and this is F, this is D, this is E, and this is G, then you see that when you do the gluings, you also have to make sure that this semantics is somehow respected.
What is the right word for power? Power? Power, thanks.
Cheers. So now if I'm gluing these things together and I am attaching these things to a semantics, first I have to make sure that the semantics attached to this thing is the same as the semantics attached to this thing. And also I have to make sure that these places are mapped to the same thing. Otherwise, in here I have a problem. Do I map this to C, to D, or to what? So, basically what I try to do is to find a general way of gluing nets together, which is is mindful about the semantics you map the nets to, and can do at the same time place gluing and transition gluing. Part of the developed in this paper comes from discussions I had also with David at ACT, last ACT, which then I further developed into something hopefully a bit more structured. So yeah, let me start with '90s, so it's not new. There are again different flavors of doing this, but it's not really important. So yeah, this is another, and a fold for us is literally just a free category generated on a net to some semantics, so some symmetric model category of some sort. So yeah, this is basically what we're doing here. So this important thing, if you have a Petri net, you can associate a free strict symmetric model category to it. With monadal functors, you can get semantics, and the underlying structure topology of a Petri net is basically an hypergraph. You can also simplify things just considering graphs here, and then you get something that really looks like a finite state machine. Instead of free symmetric model categories, you get free categories, and you just need functors to define semantics. The reason why this is relevant for us is that implementing this first row turns out to be very, very much easier than implementing the second one. So lately we have been focusing on the first row. But yeah. Okay, so the first thing I want to do to basically find a nice notion of gluing between places and transitions of a net, finding a category of Petri nets. Again, this has been done a lot of times. What I'm doing here is category with the notion of morphisms that is slightly generalized with respect to what has been done already. So this category is called Petri S, where S is the semantics. And the idea is very simple. Every object here is just a couple where the first thing is a net and the second thing is a functor that goes from the free category associated to the net to the semantics. And morphism, unsurprising, basically. So what do we have some water or something to, because this is really hard to. Oh, this. Not really. Huh? Yeah, for instance, in what we are experimenting with now, what is happening? I'm dying, help. Okay.
This is not a movable whiteboard.
Yeah. Yeah, but this whiteboard here is really not good because you have to press a lot to wipe it. So typically my semantics is, in what we are experimenting with at the moment is, for instance, Idris types and functions is the thing that we use the most. So we literally map places to data types and transitions functions between those data types.
Something like graph is to state machine as category is to something.
Yes. So the idea is that if you consider Petri nets where all markings just have at the most one tokens, and transitions just have one input place and one output place, then the underlying structure of this Petri net is basically a graph because your hyperedges are edges. And you can see this as a finite state machine. Now, the only token you have is basically used to mark the state the FSM is in. And when you see things this way, then the idea is that you don't need anymore the monoidal part of the free category because you are not interested in markings with more than one token. And so you can just compute and create the free category of the thing. And also the semantics can just be a category and you can just have a functor to the semantics. So since it turns out that the symmetric monoidal part is complicated when you implement things, this is actually a nice simplification when you want to do implementation. But yeah, basically in this case, what I'm saying is that if I have a net n, those couples I was writing there can really just be represented in this way. I have this, I have this, and I'm saying that a morphism between these two things is just, sorry, this is, a morphism between these two things is just really a functor so that this triangle commutes. So the idea is that when you map a net to another net, you want to commute with this assignment of semantics. So yeah, okay, this is another definition I have to give, which is actually simple. Oh, but no, I think it will hold, no worries. So another thing that I have to say is that in a free symmetric monoidal category, basically, there is, since this category is free, there is really like a unique, almost unique way of representing a morphism in here, modulo the equations of a free symmetric monoidal category. So the idea is that, for instance, if I have a string diagram like this in particular, okay, I can introduce like symmetries in the middle that maybe cancel out and stuff, but what is really important, in any possible way of representing this diagram, the generating morphisms that show up are always the same. So for instance, in this case, I can basically
remove the line.
yes. So what I'm basically doing here, I'm saying that for each morphism in a free symmetric monoidal category, I can set of all the generating morphisms that compose it. So in this case, this is, for instance, F and G. And yeah, you can basically prove that, you know, modulo all the equations that hold in a free symmetric model category, this thing doesn't change. So if I have F and I have G here, I can slide these things, but I cannot introduce new generating morphisms or take generating morphisms out without altering what this thing is. So I can basically associate to each morphism this kind of thing. And I'm using this later. But the idea is that if I write something like this, and at some point I will, what I mean is literally in G. So in this case, if this is, let's say, call this K, then this is, I don't know if this is clear, but there's just like a minor point that will turn.
Spell out when you write something on the whiteboard, because it's not super easy to see on the video. So
Okay.
S stands for K, I assume that you wrote there.
Yeah, okay, I will try to. Okay, so the gluings, I think that basically the important part here is that there are two big classes of gluings I found. So the idea is that I want to express gluings using these functors between these kind of things. So I want to say that a gluing of Petrinet is some particular morphism in this Petri S category with some particular properties. And I want basically to isolate two subclasses of morphisms that represent place gluing and transition gluing mainly. So the first thing I looked at is synchronizations, which is, again, way of gluing things by conflating transitions. So another thing that you will notice is that since in this framework we don't have ports, we have to specify what we are gluing. And then I will show that you can get back what we meant gluing things up to now, but like in the previous literature. But the idea is that the only thing I can really presumably glue at the moment with this kind of stuff we developed is transitions and places within the same net. So for instance, I don't know if you can see this. Yeah, but yeah, it's. Yes, perfect. So, okay, in this case, I'm basically saying, what does it mean to synchronize things? What does it mean to synchronize transitions? So, first things first, synchronization as a concept that makes sense only when you synchronize transitions, because places are considered, at least in this framework, as containers of resources. They are inherently asynchronous, and I didn't really even have an interpretation of what it means to synchronize on places. But on transitions, the idea of synchronizing is that you want to say that, for instance, when this thing fires, that something else has to fire in the net. And there are basically two ways to do it. The first way is by synchronizing by sharing resources. So in a case like this, this means that you want to say, for instance, when G fires, then K fires, consuming the resources just produced by G. And it's here. So you know when G fires, K fires, and no doubt the net becomes this kind of thing. Because, yeah, this has two outbound arrows and this has two inbound arrows. But when you consider the conflation of these two transitions in the gluing, then this thing is exactly consuming the things produced by this one. So you kind of thing here. And the other way of synchronizing transitions is that by not sharing resources. So you want to say when G fires, then H fires, and then you have something like this, where basically, you know, all the inbound edges of both things get conflated, and same thing is for the outbound things. But now you can also obtain like mixed things, where you basically say, okay, G fires, I want to fire, then I also want to fire K, or the resources that these two things consumed. And so you can glue these things together. Basically, modeling this thing is quite easy because this is what we say. We say that a net M is a synchronization of a net N if there is a morphism between them that is injecting generating objects, faithful. And this last row has to do with what I wrote. But is what does it mean? It means that again, I want to show that a morphism between these things in this category is just a functor from the free category built on M to the free category built on N, which commutes with the semantics. But importantly, since this thing is a functor between their free categories, I'm in principle free to map morphism, so transitions of this net, morphisms of these things that are computations, runs of these nets. And that's how we do synchronization on this. So for instance, I'm really saying that the gluing of this net is this. And what I'm doing is I'm saying that this, if this transition is mapped to G in the semantics, and this is mapped to K in the semantics, then this generating morphism is mapped to G after K in the semantics. And so you see that you can express this as a morphism that goes from this net to this net. And in here it's similar. I'm saying, OK, this transition here corresponds to the monoidal product of these generating morphisms. So it's mapped to this monoidal product here. And obviously, you want to give some definitions to make this thing sensible. So you want this functor to be injective objects, and the reason.
Can you maybe zoom in a bit, like just this big that it's really easy to read them?
Let me see if I can. Is injective on generating objects, and basically you want this because, as I said, if you think about synchronizations as something that happens on transitions, you really don't want to do anything on objects. You want to leave the objects like as they are. I restrict this F to be injective on objects. Then you want F to be faithful. And the reason for this is that, in general, if you think about the net M as a gluing of the net N, you would like to say that every transition in M is a way of squeezing transitions of N together. And in this case, require because it doesn't really make any sense to say that two different transitions in here are mapped to the same computation in here. It's like you say, I'm gluing things and I'm taking copies of this gluing. And I wanted to rule this out. And the third thing here, where I use that notation I wrote there, is basically saying that if you just take these two things, then you can say that, for instance, the net consisting of just one place and no transition is a synchronization of any net. Because you are just saying, OK, I'm deleting all the transitions that I have. But this is not doesn't conform to what a synchronization is. When you synchronize transitions, you don't want to delete them. You just.
How can you delete in a functor?
So the idea is you have that this functor goes from here to here. The idea and the underlying idea of this thing is that every generating morphism in here should correspond to a synchronization, so a way of conflating generating morphisms in here. But if you just have these two properties like you have here, then what happens is that the net with no generators in here is a valid synchronization of any net. So like you are able to say, if you just assume the first two properties, that this net with just two places is a synchronization of this net. And this doesn't really make sense. What you would like to say is something like, I have this thing here that is corresponding to synchronizing these two things, for instance. And to do this, you basically have to require this condition that is saying that whatever you map these transitions to, if you consider all these mappings, basically all the generating morphisms of this net are used to build this mapping. So yeah, that's why you have the third thing. Another interesting thing is that you require f to be injective on generating objects and not bijective on generating objects to get rid of this kind of situation here. It's visible more or less. I have this net and I synchronize this transition and this transition. What I get is this. And now you can see that just using the rules of how you build these functors and whatever, you basically get some places which are isolated and are completely useless. Like this place will basically float around forever. And the reason why you require the functor to be injective and not bijective is because if you have injectivity, then you can forget of these places. The functorial laws tell you that you can delete places only when they are isolated. No.
You don't want it to do that?
No, because I actually didn't say that, but all my functors in this category are functors of this form which send generating objects to generating objects. And the reason why I read this is because I couldn't give any meaningful interpretation of what it means to send a place to a product of places. But if there is any, it would be really interesting to see what happens when we relax things a bit. I always focused also on how operationally this thing, no, operationally is probably not the right word, but this thing works, these things work in practice. So in this case, it's very easy. What I mean, in practice, if I have this net and I want to synchronize some of these transitions, I just want to think about what happens on the net part. I don't want to have to manually specify the semantics of this thing here, if this is a net synchronization. And basically what this lemma is, which is actually obvious, is that if you have a semantics like this, this is f, then if this net m, if I have a functor here, which is a synchronization, then I can automatically obtain a functor here which mutes this by just taking this composition. So the idea is that you don't have to manually specify these semantics functors. You can infer them automatically just by looking at what happens here. And then we do identification, which is the other kind of thing, so gluing along places mainly. And the idea of synchronization is this. Synchronization really is about getting rid of redundant information. For instance, if you see this in this net, you have these two transitions f, which are mapped to the same thing in the semantics. So for us, they are really doing the same thing. And what we would like to do is to convert them to one transition. So this is not a synchronization. If I were synchronizing things, I would have a 2 on these edges, because I would be conflating things, while in this case, I'm really saying, no, actually, these are redundant, so I just want to take one. Similarly, in here, this thing is saying G is producing a token in C and a token in C. That basically means 2 tokens in C. So I would like to be able to conflate this C. But okay, this thing is you see, age is consuming a token from C and a token from C, and so 2 tokens from C. It turns out that you can express this thing as another kind of functors with some morphisms with some particular properties in this formalism. By the way, you can iterate this approach and, for instance, say, okay, this is really difficult. I can say, okay, I have this net, And you see that this subnet and this subnet is the same thing. You can iterate the thing and saying, OK, I want to conflate them into one. I want to identify them. So in our formalism, basically, we say that a net n is an identification of a net m if there is a morphism that this thing goes from m to n. So it goes on the other side of the thing. Let's see. So before we say that was the synchronization of n. Now things go in the other direction. If I have this, this is an identification of. And the way it works is you literally have a Petri net O, which serves as a witness, and a couple of functors called left and right that go from this thing to f of m, yes, to this thing, such that this functor f, this morphism f here, which correspond to a functor f between these two things, is the coequalizer of L and R here. So the real way you have to think about this is that you have a witness net O, and then you have these L and R that send generating objects to generating objects and generating morphisms to generating morphisms that are telling you for each object of this which objects you want to identify, and for each transition which transitions you want to identify. And then you say, OK, this F is the coequalizer of these two things. And obviously, you also require that these L and R commute with the semantics of M. And this condition is basically saying that you identify only things that go to the same thing in the semantics. If I have something like this, and this place goes to A, and this place goes to B, and A is different from B, then you can't identify them, because it doesn't make any sense in this framework to identify things that go into things in the semantics. And yeah, I mean, that's basically it. The cool thing about identifications is that, I mean, they use coequalizers, which are not the best thing when you do implementation, because coequalizers are actually quotients. But it turns out that if you want to identify just a finite number of places, then that's not a problem. Because if your quotient, if your net O, which is the witness net, is a net with places and no transitions, then there is a convenient way to build these identifications without using quotients. So the first thing one notices is that if this net O has only one place, then basically these L and R are sending this place to different places of M, then the coequalizer of these two functors is just obtained by renamed all the instances of one of the two objects with the other. And when you have a finite number of places in O, then you see that you can basically build this kind of thing where you say, I identify things in each step, I just identify two things until I identify all of them.
Can you say again the rules on the two functors that you're co-equalizing?
Yeah.
Two symmetric monadic functors? Or?
No, they are two symmetric monadic functors which send generating objects to generating objects, and moreover are transition preserving. Transition preserving T is a generating object, then this gets sent to sigma G sigma prime, where G is a generating objects in the target category, and these two things are just symmetries. So the real problem when you map things to other things in symmetric monadic categories is that you have all these wires on the sides that sometimes have to be permuted. So this means it morally sends generating morphisms to generating morphisms. But if you just say this, it becomes super reductive. So instead you say it sends generating morphisms to generating morphisms pre and post composes with permutations, with symmetries. You see that what this really means from a practical point of view is that these left and right functors really arise from the topology of the nets. These are really like way of mapping entities of a net to another net. So these functors are not mapping anything to computation. They're really mapping topological elements to topological elements. Yeah, and that's basically it. And another cool thing is that now we would like to recover what it means gluing different nets. So we would like to recover the usual approach where you have nets with ports, and you compose the ports, and you do things. Well, you can see that this is doable because this Petri S category has a very simple monoidal structure on it, and the monoidal structure is just coming from the coproduct. So what we are doing is saying that if you have a net M and a net N, I can consider the net where I put all the transitions and all the places in the same box. It's even difficult to draw because it's really saying if I have this net and I have this other net, then I can consider these two things as a unique net, like the coproduct structure. You see that now I can imprint things of different nets by first composing the nets and consider them as one, and then performing the gluing. And the cool thing about this is that when you look at the details, the coequalizers that I showed before become push-outs. So what you really do is that when you say, okay, I want to glue stuff in this net with stuff in this net. So my L and R go like this now. Well, I squeeze everything into this thing, which is the coproduct of the two, and then I do the gluing of the compositions, which is a coequalizer. Well, but the coequalizer of the product is the push-out. And so basically you recover the push-out approach that has been really shown. And I didn't really work out the details because it's a bit complicated, but you can also recover the way, for instance, Pavel and other people were gluing synchronizing transitions. So what they did is that they had nets with these ports I was showing before. And when you glue using their formalism, the idea is that you also have to synchronize on the number of firings. So for instance, this thing is consuming 2 tokens here and 1 token here. So this thing will have to fire 3 times when you synchronize to satisfy this request. And so what you get is this. And this thing basically represents the event of these things firing 2 times, 3 times, this firing 1 time, and this firing 1 time. All the details are spelled out in the paper. What we can do in our framework is just like substituting these black dots with places, which makes sense because in our framework everything needs to have a specified semantics. And then you basically first identify the places, and once you identify the places, you can glue transitions together. And you see that the gluing you can do here is exactly what I was saying before. You have F, tensor F, and then H tensor K. So you're saying F fires 3 times, H fires 1 time, and K fires 1 time. And then, yeah, I also showed that obviously, I mean, this really comes from the fact that we are considering like slice categories when we do things. You can change the semantics. You can take products of the semantics and all these kind of things. So you can also change the underlying semantic of the net. And basically, when you do these kind of changes, say really all these triangles where all the colimits part is built on top and all those things is just like dangling down, it doesn't really matter. All these gluings and things are preserved when you change semantics. So yeah, that's basically it. And then what I wanted really to look into is during these days is I would really like to find a graphical formalism to express these net and transition gluings way. And another thing to look at is what happens if we generalize these morphisms from being functors to probably being profunctors. So this is something I was discussing again with David at ACT, but using profunctors instead of functors in this setting may give us a more relaxed notion of morphisms, which can be useful also in, let's say, a dynamical setting. A dynamical setting is when I have to morph this Petrinet to this Petrinet. I also have a computation of the net already. So if you look at how Statebox works, this thing is like your Statebox program, and as you execute it, you get this morphism in the free symmetric monodal category. Now you want to map this to something else, then these morphisms have to be, migrated to the new thing, which you can always do in this direction. But when you are here, you have a selected morphism here, then it's not obvious that you can find something here that is in the pre-image of this morphism, because this functor may be not full. So you see that we need to relax these kind of things to make them work. And so yeah, that's basically it. Yeah. So. I suppose hopefully there are questions, because that was.
I mean, as you say, there are many different ways of categorifying Petri nets. I guess what you want is something that works for application that you want.
Yeah.
And this that you have quite clearly. So like, because you make a few design choices, but it is not clear to me like what kind of application this should be.
So our application is this is really important. Basically, what we are really interested in is the process semantics of Petri nets. Like if you look at, for instance, the synchronization like done by attaching ports to transitions of a different sort, that thing really has an observational semantics flavor. While we don't need that, because literally that our application is we use Petri nets just to present free symmetric monodal categories, and then we map these free symmetric monodal categories to semantics using symmetric monodal functors. So imagine this, because this is really the way it works. You draw a Petri net representing some process. Once you are satisfied with this net, you literally click on each transition in place and say, okay, this is this data type, this is this function. Then you press a button, and you automatically obtain the protocol generated from the Petri net, which allows you to fire a transition. And every time you fire a transition, you are actually composing the corresponding function to your state. And the way this works is under the hood is literally generates the free symmetric monodal category, generates a functor to your target category, and then gives you all the kind of like boilerplate around it to easily compose these things when you call things.
So I mean, it looks like every time you have to generate a free symmetric monodal category. So how efficient this is, because it looks like generating a free symmetric monodal
every time you generate a free symmetric monodal functor, but free symmetric monodal category, you already have it in your system. So,
okay, so that's a once.
Yes.
Okay.
But also, also the symmetric monodal functor is once, in the sense that after you generate it, then you have this API, and you can call this Petri net and compose everything, and the functor stays fixed, is always the same. So yeah. But at the moment, yeah, we are still like implementing this kind of thing, and we didn't really focus on efficiency too much. There will be a lot of optimization to do at some point, but at the moment, we just want a proof of concept that this thing works. It's taking a long time also because we are working in a formally verified setting. So basically, we are literally typing down what a category is, what a functor is, like taking the definitions from the MEC lane and implementing them like verbatim. The good thing is that if the underlying theory works, then this thing should work. Otherwise, that would be a problem. Yeah, so.
This is probably a stupid question, but are your synchronizations something to do with simulations of state machines?
Where?
Simulations of state machines.
Yeah, I missed the first bit.
A relation that says everything here has a corresponding firing over here. Okay.
Yes, there may be a relation, but then again, I looked into all the bisimulation stuff in the beginning, but then I just stopped looking into that because, again, their notion of semantics is really not the same of our notion of process semantics. So, I mean, that's the real problem. Like when you consider Petri nets just as Petri nets, you know, it makes a lot of sense to say, yeah, this kind of thing gets mapped to this other kind of thing, but when you construct the corresponding three symmetric monodal categories and you have these functors, this may make no sense. So I think has obscured for a lot of time what was the difference between synchronization and identification is that if you just look at the nets and you forget about labels that are denoting the images in the semantics of these things, then you say, okay, I'm just identifying transitions. These are just like two ways of identifying transitions and places which are more or less the same thing. But that's really not the case. When you map the semantics, you see, oh, actually, one way of doing this is an injective functor, and the other way is a colimit. So there's a completely different beasts that get conflated in the same thing when you just look at Petri nets. So I would be interested in looking at what bisimulation means in this setting, but yeah. Other questions? Well, then I guess that's it. Thank you.